Yeah. So we'll be doing problem 2 on week three's worksheet 2.2. Um, so first off, this is gonna be a hypercube problem. Austin has n is greater than 2 light bulbs in a row, all turned off. Every second, Austin performs a move where Austin either turns a light bulb on or turns a light bulb off. Show that for any n, there's a sequence of moves that Austin can make such that each possible configuration of light bulbs being on or off has occurred exactly once, and such that the last move causes all light bulbs to be off. And then part A asks, each of the n light bulbs is either on or off. How should we represent the light bulb states mathematically? So, part A, sorry. We can represent each state as an n, length n, bit string. Sorry for my bad handwriting. So, for example, if we had n equals 5, and let's say this is this blank would correspond to the first light bulb, second light bulb, third light bulb, fourth light bulb, fifth light bulb, and the bit string. So the value could be 0 or 1. So maybe 0, 1, 0, 0, 0. And the zeros would correspond to the light bulb being off, and 1 would correspond to the light bulbs being on. So this would mean that all the light bulbs except for the second one are off. Okay, let's move on to the second question. Second question asks, frame the problem in terms of hypercubes. So hypercubes are related to bit strings. The relation is that I want to draw a 2D hypercube here. The relation is that each edge of the hypercube corresponds to a bit string. So we can label the hypercube in this way. And the reason this works is because when you generate a new hypercube, and this is related to the next part of the problem, to generate a new hypercube, you simply copy the current one, and then you connect the corresponding edges that have the same bit string values. And then what you do is you connect these. So maybe I want to redraw this. Sorry for the bad drawing. You would connect them, and then, for example, this point here would be 0, 0, 1, and this point here would be 1, 0, 1. And this works because, and then this will be 1, 0, 0, and this will be 0, 0, 0. So the first copy would be zeros at the front, and the second copy you would add a 1 at the front. And that's how you make, that's how you go up in dimensions for hypercubes. So now that we know how hypercubes kind of correspond to bit strings. So each edge on the hypercube would be a bit string. I mean, sorry, each vertex on the hypercube would be a bit string. So it would be like 0, 0, 0, 1, 1, 0, 1, 1. And so it would be like 0, 0 means both light bulbs are off. 0, 1 means one of the light bulbs is on. And then this would, the 1, 1 would mean both light bulbs are on. So how can we frame this problem in terms of hypercubes? Well, we need to find something that each possible configuration of a light bulb being on or off has occurred exactly once, and Austin ends up in a place such that the light bulbs are all off. So he starts and ends in the same place. The light bulbs are off. This is a cycle. So he starts and ends in the same place, and the light bulbs are off. And we can see here that each edge corresponds to an action of turning one light bulb on or off. Each edge between two vertices in a hypercube corresponds to one of these bits being flipped on or off. So we can see here 0, this this second bit is flipped to positive, and then we can see here that the first bit is flipped to positive. So okay, frame it as a cycle, and this cycle must visit all states. In other words, all vertices in the hypercube. He must, and so this is a Hamiltonian hypercube. Hamiltonian cycle, sorry. Hamiltonian cycle. This is a Hamiltonian cycle. It's a cycle that visits all the vertices once. And that's exactly what the problem is looking for. Okay. Let's see. Let us solve the problem by showing the property of hypercubes. So what do we need to do? We need to show that basically if we show the hypercubes have Hamiltonian cycles, then we're good. We can then we can say that the problem can be solved because the problem has been framed in terms of hypercubes. So in order to show that we have a Hamiltonian cycle on hypercubes, Hamiltonian, I'm just going to say Ham cycle in hypercubes. So this is a proof question. We must show a property of the hypercubes, which is Hamiltonian cycle. In order to show this, I'm going to use a proof by induction. Let's see. Let's start off with our inductive hypothesis. So what is the hypothesis? Sorry about that. Hypothesis is that for n, or for any k, for some k, hypercube of k dimensions has Hamiltonian cycle. Okay. So let's start for the base case. Also, for dimensions, I'm talking about the number of bits in the bit string. So this would be a two-dimensional hypercube right here. This would be a two-dimensional hypercube. And then something like this would be a three-dimensional hypercube because the vertices would have 3 bits in them. Okay. So let's start by showing the base case. Base case is n equals 2 because in the problem we can see specified here that n is greater than or equal to 2. So we can start with n equals 2. And for n equals 2, we have this square right here. So I'm going to copy that here. We can kind of go, sorry, that should be 1 there, and 1, 0. We can kind of go this way, and this will be a cycle that covers all the vertices. We could also go the opposite way, but both ways are fine. Okay, so n equals 2 is solved. I'm gonna add a new page here, and now all that's left is to prove the inductive step. And the inductive step for inductive proofs usually makes use of the inductive hypothesis, which is that for some k, the hypercube of k dimensions has Hamiltonian cycle. So just kind of for ease of proof, for ease of drawing, I'm just gonna draw the case for 2, but this without loss of generalization. So these will be connected. These will be connected by the corresponding bit strings that are the same. 1 1 1 0 0 0 0. So on a 3D hypercube, there'll be ones here and zeros here, and that's how 3D hypercube work. You connect them, and then you put a 0 in front of this one and 1 in front of this one. Anyways, so we can start here. We can start on 0 0, 0 0 0, and then because we know, so let's say k equals 2, for example, without loss of generalization. Let's say for some k, we can make a hypercube because of the inductive hypothesis. So before we complete the Hamiltonian cycle on the degree k hypercube, we're going to stop here, and we are going to cross over to the corresponding edge on the other hypercube, right? So we're going to go from so there's going to be 0 something 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 something, that's length k. This part is going to be length k. So for example, in this 2D case, it'll be 0 1 0, and then we're going to cross over to 1 0. So we're going to go here, 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 and then before we complete the Hamiltonian cycle on the degree k, we're going to cross over on the very last vertex before we complete the cycle to its corresponding edge on the other hypercube. So this would be 1 1 1 0, and from 1 1 0, we're gonna do a Hamiltonian cycle, but this time it's gonna end at 1 0 0, and we can do this like so. A fun fact about the Hamiltonian cycles is that you can start any edge and make a Hamiltonian cycle just because a hypercube is symmetric. It's the same from all directions. A square is it doesn't really matter what vertex you're on. All of them are connected to their corresponding edges. So yeah, we're gonna make another Hamiltonian cycle, and we're gonna end at the vertex we started on, at the corresponding to the vertex we started on, and then we're gonna go back to the vertex we started on, 0 0 0. So we're gonna start at 0 0 0, and then make a Hamiltonian cycle, and then stop short on the last vertex before completing the Hamiltonian cycle, and then cross over to the other hypercube, and then we're gonna make another Hamiltonian cycle, stop short on the last vertex, and then cross over to the original hypercube, and this will cover all the edges this way. And we also end at 0 0 0. So I've just proved the case for k equals 2, but you can see here that nothing I did involves the fact that it could be generalized to 1 0 0. We could add more zeros here, and it would still be the same thing. We just end at the edge before the last edge before the end of the hypercube. Before the end of the Hamiltonian cycle. So now I have proved the case for k plus 1 has been proved. Because to make the k plus 1 hypercube, you combine two of the same hypercubes through their corresponding edges, and I use that property to make Hamiltonian cycle on the first cube, stop short, cross over, cover all the edges on the other hypercube, stop short again, and then cross over back to the original point. And this will make a Hamiltonian cycle covering all the edges on the new k plus 1 hypercube. Covering all vertices. And therefore, we have a Hamiltonian cycle exists on all hypercubes because we proved it for k plus 1. And now we're done. Since we proved the property that hypercubes exist on all the Hamiltonian cycles exist on all hypercubes, we have that the original problem, which was framed as in terms of hypercubes, is also proven. Okay.